So we're going to have a look now at covalent bonding. Having previously looked at ionic bonding, we're going to look at covalent bonding. So if we just think about what's happening in covalent bonding, then if we think about two non-metal atoms here, so I've labelled these as NM, what they're going to do is share electrons with each other. Rather than exchange them like they do in ionic bonding, we're going to share electrons. And actually what happens is the outer electron shells for non-metal atoms, for two or more non-metal atoms, overlap. And a pair, or more than one pair, but they're pairs of electrons, end up going in the overlap region between them. And this shared pair of electrons we call a covalent bond. So that's a shared pair of electrons. What's actually happening here, if we think a little bit further about what's present in an atom, then we've got a nucleus in the middle of each of these atoms, which has a positive charge. And then in between those, we've got a pair of electrons. And remember, electrons have a negative charge. So there is an attraction between the nucleus of each atom and the shared pair of electrons. And it's actually an electrostatic attraction. Because the nucleus and the shared pair of electrons are so close to each other, it's an even stronger attraction than that between positive and negative ions. So let's have a look at how this works in practice. So I'm going to look at what happens in the Cl2 molecule. So I'm first of all going to draw two chlorine atoms with their outer shells. Now chlorine is in group 7, so it's going to have 7 outer shell electrons. And like we did with the ionic bonding, we're going to draw one of the atoms with crosses for the electrons and one of the atoms with circles or dots for the electrons. Now, if we look here, this chlorine atom needs 1 electron. Therefore, it's going to have to share 1 electron. And the same thing here. This needs 1 electron, and therefore it's going to have to share 1 electron. So we've drawn the outer shell electrons, and we've worked out how many they're going to share. So now let's draw the chlorine molecule with the overlap between the electron shells. So we've got our overlap region, and because we're sharing this chlorine atom is sharing 1 electron, and this chlorine atom is sharing 1 electron, we're going to put 1 electron from each in the overlap region. And then we'll put the remaining electrons on the outer shell. So I put 1 of these electrons into the shared region, and then we had 6 left. We're going to have the same thing here. So we could also draw a ball and stick diagram of this, where we draw the 2 chlorine atoms with a line between them, and this line represents a covalent bond, or a shared pair of electrons. So the reason this happens is if we look at one of our chlorine atoms, including the overlap region, it's now got 8 electrons. So therefore it's stable. And look at this side, including the overlap region, this chlorine atom has got 8 electrons. Let's have a look at a case involving hydrogen now. So we're going to look actually immediately at the hydrogen molecule, so the H2 molecule. So hydrogen is a special case. It doesn't really have a group number, but hydrogen has just 1 electron. And we remember from our earlier work that because hydrogen is such a small atom, it in fact, unlike all of the other atoms, needs only just 1 more electron. So each of these need 1 electron, and therefore they are both going to share 1 electron. Let's now draw the overlap region. A hydrogen atom and a hydrogen atom, they've overlapped. Because they both are going to share 1 electron, it's going to put 1 electron into the overlap region, and this one has 1 electron into the overlap region. And because hydrogen is such a small atom, both of those hydrogen atoms are now considered to be stable. We can draw the ball and stick diagram for this as a hydrogen atom bonded to a hydrogen atom. Okay, let's now have a look at a compound where we've got, compound where we've got two different atoms. So HCl. Our first step again, hydrogen, it's got 1 electron. Chlorine, which we did earlier, has got 7 electrons in its outer shell. We know that because it's in group 7. This needs 1 electron, therefore it's going to share 1 electron. This atom needs 1 electron, therefore it's going to share 1 electron. Okay, so we've identified how many electrons they're going to share. Let's draw the overlap region. This is going to share 1 of its electrons, goes into the overlap region, and this is going to share 1 of its electrons, it goes into the overlap region. Any remaining electrons, there are none on here because that one's been used, this one's been used, but we've got 6 circles or 6 dots left here. Let's draw our ball and stick diagram, which is a hydrogen bonded to a chlorine atom. Okay, let's look at a slightly more complicated example now. We're going to have a look at a water molecule. So water has the formula H2O. Same process again, hydrogen, and this time I'm going to put the oxygen atom in the middle of 2 hydrogen atoms. So the odd one out usually goes in the middle in one of these molecules. Hydrogen is our special case. It's got 1 electron. I'm going to show both of those with crosses. Oxygen is in group 6, so I'm going to put 6 electrons in its outer shell. 1, 2, 3, 4, 5, 6. So each hydrogen atom needs 1 electron, therefore it's going to share 1 electron. So this one needs 1 electron, and it's going to share 1 electron. This oxygen atom needs 2 electrons, and therefore it's going to share 2 electrons. Let's draw the overlap regions like this. So this one is going to share 1 electron in the overlap region. Now oxygen is going to share 2 electrons, but it's got 2 overlap regions, so it's going to share 1 of its electrons in this overlap region and then 1 in here. This hydrogen is obviously sharing that electron there, and then we've got the remaining electrons that go on there. And if we have a look at each atom, hydrogen there's got 2 electrons, including in the overlap region. This oxygen's got 1, 2, 3, 4, 5, 6, 7, 8. So this is a full outer shell, and this hydrogen has got 2 here. We could draw the ball and stick diagram for this. A H bonded to a O bonded to a H. Okay, 2 more examples. PH3, molecule you might not come across very often, it's called phosphine, but we can work out the same process. So we'll start with phosphorus in the middle and hydrogen around the outside. So phosphorus is in group 5, it's got 5 electrons in its outer shell. Hydrogen has got 1 electron. So each of these hydrogens needs 1 electron, and therefore each hydrogen is going to share 1 electron. But if we have a look at the phosphorus needs 3 electrons. It needs 1 there, 1 there, and 1 there. And therefore it's going to share 3 electrons. So now let's draw the overlap region. So this hydrogen is going to share 1 electron with this phosphorus electron here, and so on and so on. And then we have all of our atoms have full outer shells. If we draw the ball and stick diagram, then it's going to look like that. So for our final example, we're going to look at carbon dioxide, and this is going to introduce a double bond to us. So carbon dioxide, 1 carbon atom, 2 oxygen atoms. We put the odd one out in the middle, and then we start putting the electrons on. Oxygen is in group 6, so I'm going to give it 6 electrons. Carbon is in group 4, so I'm going to give it 4 outer shell electrons, and this oxygen here with 6 outer shell electrons. So this atom needs 2 electrons, this one needs 2 electrons, this carbon needs 4 electrons. Therefore, this is going to share 2 electrons, this is going to share 2 electrons, and this is going to share 2 electrons. So when we draw our overlap region, or our diagram with our overlap regions in it, then this one's going to be slightly different. If we look at the central carbon atom, this one, sorry, there's a mistake there. That should be share 4 electrons. So this carbon atom here is going to need to share 4 electrons. And because there's 2 oxygens on either side, it's going to share 2 with each, because this oxygen needs to share 2. So this oxygen is going to have to put 2 of its electrons into this overlap region. And we've got a cross, a dot, a cross, and a dot. The same thing is going to happen on this side. If we look at any electrons left over, all of carbon's electrons have been used up in the overlap regions, and then each of our oxygens has got 4 left over. And then this gives us what's called a double bond, because we've got 2 shared pairs of electrons. Like that. Thank you very much.